All right, so good morning to everybody. We're going to talk about the sections that were kind of introduced on Tuesday. So sections 1.1, 1.2, and 1.3 in particular. And if we have time, we'll take a look at some applications. So I wanted to show you on the My Open Math site, I had inadvertently switched these two assignments. So the calendar is now correct. The lyrics homework is due on Tuesday and the weekly problem set is due on Thursday. So we're going to continue to do it this way, have the lyrics homework due before the weekly homework. It serves as a way to get ready for the weekly homework. So this is kind of your do it to complete it, get it right, use those problems to help you with the weekly homework. I think I have the rest of the schedule written out here. Let me make sure it shows up before I tell you that. So midterm exam number 1 is Thursday, February 24th. Spring break is the week of March 14th. Second midterm exam is April 7th, and these are going to be on Thursdays. And then the final exam is Tuesday, May 10th. Okay, so those dates will probably not change. If they do change, I'll give you ample notice for that. But I think you can kind of continue this pattern once we start doing more assignments. The lyrics homework due on Tuesdays, weekly problem sets due on Thursdays. So as I said, you can submit these one of two ways. You can take the problems that you see here. So this is the set for the first one. Do the appropriate number. So you have a choice on some of these. And then the directions here say you can turn it in during class or you can upload it to My Open Math. So it's kind of a nod to how things were done online. But to me, if you want to write it out, turn it in class, that's perfectly fine as well. It's just if you do the upload option, you have until 11 p.m. that day to do it. So either way, you'll get it graded and I'll get back to you next class period. So for this one, where, as I said before, first question is not really a question. It's essentially upload your work. So once you get it all done, save it on your computer, upload your work. So for us, we're not doing any actual online homework through My Open Math. You're uploading a few things, but the actual online homework is done in lyrics. All right. So let's go over a few things in section 1.1, do a few more examples. I'll get some definitions, take a look at some theorems. So let me go to the whiteboard here. All right. So in section 1.1, oh, there we are. Sometimes forget where you are. Okay. So in section 1.1, this is essentially an introduction to systems of linear equations. And we talked in class about what we mean by a linear system. So it's not the number of variables, it's the fact that all the variables are to the first power. So when we write these down in general, we talk about coefficients. See, I haven't written in a while, this is bad. And if you start writing these down in general, it's a sub 1 through however many coefficients you have. So a sub n would be the last one, and then variables. You can use x and y and z for up to 3 variables, but in general, you're going to write these down as x sub 1 through x sub n. And then you'll have a certain number of equations. So a general system will have essentially m equations and n variables. So you start converting these to matrices. The matrix that you're going to look at is matrix A. It's going to be an m by n matrix. So the first number tells us how many equations we have. Second number tells us how many variables we have. So we had done this example in class. I'll just give you another one here. So if I just give you a single linear equation in 3 variables, I ask you to solve this. You say there's probably not much to solve. You can solve for x sub 1 in terms of the other 2 variables. You can solve for x sub 2 in terms of the other 2 variables. But if you're going to determine something uniquely, you need to know 2 of the 3 variables so you can determine the third. So there are a couple different ways you can write down what we would call a general solution for this. And this is where that idea of a parameter comes in. Now, our book uses letters like S and T to represent parameters. You could just say x sub 3 is a parameter. You can say x sub 2 is a parameter. In this one, you're going to need a choice of 2 parameters. So let's go ahead and call x sub 3 t and x sub 2 s. By doing this, this becomes t, this becomes x, and then you say, how can I write the other variable in terms of those parameters? So replacing x sub 3 with t and x sub 2 with s, you could then solve for x sub 1. So 5 minus 7t, moving that to the other side, and then plus 4s. And that's how you would write your solution. So 1 equation, but 3 variables. If you write it as an ordered triple, this is the expression for x sub 1 in terms of the 2 parameters. It's 4s. And then remember, x sub 2 is s, so that's the first parameter, and then second parameter was t. So if you want to write it as an ordered triple, you can. You don't have to write it that way as long as you've identified each of the 3 variables in terms of the 2 parameters. So what this means is you need to designate an s and a t before you can determine the third variable. And we had also talked about in class on Tuesday, what does this look like if you want a graph of it with up to 3 variables? You can kind of picture what the graph looks like. We know the graph's going to be a plane. And this is essentially describing all the points on a plane. So if you've had third semester calculus before, you've seen how to do equations of planes. So these numbers that you see here would help you identify what that equation is going to look like. Okay, now we're not going to be graphing planes, so nothing to worry about here. We're just going to work with these algebraically. Once we get past 3 variables, we're going to be able to see it anyway. So 2 equations, line, or sorry, 2 variables, line, 3 variables, plane, 4 variables, 4 dimensions. And we talked about systems that have solutions. And those are what we call the consistent systems. So I'll say solution or solutions exist because you could have an infinite number of solutions here. Any system that does not have a solution is called inconsistent. So in the cases that we can actually see, 2 variables, lines are parallel. In 3 variables, I showed you a couple of different pictures on Tuesday. You can have all 3 planes being parallel. You can have 2 planes, and then the third plane intersects the 2 individually, but not all at the same time. So think ceiling, floor, wall, instead of wall, wall, floor, where you have the unique solution. The other thing to consider is 2 walls come together. When 2 walls come together, and you saw my pictures on Tuesday, they are not very good, but it's like the pages of the book come together. Open up the pages, we're right along that line right there. So in that particular case, you're going to have more than 1 solution. We can write down a general solution in terms of a parameter. So we're going to try to solve these systems using our algebraic methods, and that's where this idea of the row operations come in. So to review the row operations very quickly here, there are 3 of them that you can apply to the system that rewrites the system into an equivalent system. So one of them is to swap rows. So row 1 can become row 2 can become row 1. Doesn't change the solution to the system. Another one is you can take a multiple of a row. So if you have, for example, x of 1 minus 4x of 2 plus 7x of 3 is equal to 5, I can multiply all the terms by 2. Once again, it doesn't change the solution. It's just a constant multiple of what you start with. So those 2 are done to kind of get your matrix in a particular form. But the most commonly used row operation is to take a multiple of a row, add it to another row, and then in the system, that row can be replaced. So if I take, for example, a multiple of equation 2, add it to equation 3, I can replace either equation 2 or equation 3 with that new equation. And if you're familiar with the Gaussian elimination process, that's exactly what we're trying to do. We're trying to get a system that has 2 variables, a system that has 3 variables, and get it in a form in which one of the equations is going to tell us what one of the variables is. So this is the one that's used most often. We saw in the calculator, the TI-83-4s, they also have these individual commands that you could also apply to a matrix. So these are the row operations that produce equivalent systems. So equivalent systems are like equivalent equations. The solution to the original system and the solution to the system you get after row operations will be exactly the same. So if you have a system, you can, of course, apply the row operations without a matrix, but as we have seen, it's easier to keep track of things if you have a matrix. And we call this an augmented matrix because you take the coefficients and you augment it with the answers, so 4 and 6. Some books include the dotted line, some books don't. I like to include it just to remind myself that 4 and 6 are the answers that you would get from the original system. But as you can see, this is a 2 variable system, 2 equations, 2 unknowns. So you have 2 rows. If it's an augmented matrix, it's 3 columns. So 1 column for the answers, and then 2 columns, 1 for each variable. If you worked with matrix operations before, we're going to see in the next chapter how to write this as a product of matrices. But for now, this allows us to use the row operations and identify what do you do to the first row, what do you do to the second row, what am I adding them together. So we know that if we want to solve this, we might have a 0 here. So we say, how do I produce a 0 here? I would take 2 times the first row. I would add to the second row. That would produce a 0 in this slot right here, which means you're eliminating x from the second equation. And then usually the notation looks like this. 2 times the first row plus the second row is going to replace the second row. So if I do that, I think I can do this without writing too much more down. So 2 times the first row plus -2 would give us 0. 2 times the first row plus 3 would give us 5. 4 times 2 is 8. 8 plus 6 is 14. So these 2 matrices are both going to help us find the solution to the system. Now, this is, as we talked about, known as row echelon form, if there's a 1 in the slot. So the next answer here would be, again, terrible board management. I gotta do a better job here. Oh, man. Good news is, if this is all one consistent line, yeah, it can go away. So now I take 1/5 times row 2 if I want to get a 1 in the slot right here. So there is your matrix in what we call row echelon form. Row echelon form has 1s as far left in each row as possible. And then all the other entries are 0 below where you see the 1. So this is considered to be row echelon form. And I get really lazy, unfortunately. REF means row echelon form. So I should write it out at least once, and then you can abbreviate. So I will do that for you here. Oops, row echelon form. And what's the advantage of row echelon form? One of the equations gives you the value of that variable, and then you can either do more row operations to make this entry a 0, or you could do back substitution either way. But this is by definition row echelon form. Right, so Gina, if you want to take a screenshot here, I'm going to be, I'll save it and post it as well, but I need more room. So I'll go ahead and do that real fast if you want.
I got it.
Okay, thanks. That's the problem with Zoom is you have a limited amount of space and you can't keep it up. So it's essentially a screenshot. All right, let's do an actual example here with 3 variables. So I'm going to call them X, Y, and Z. All right, so 3 equations and 3 unknowns. So if we have a consistent system here, that means there will be a solution or an infinite number of a unique solution or an infinite number of solutions. If we have an inconsistent system, then as we're doing the row operations, we'll end up with an equation that is false. For example, 0 is equal to 1. And then you could say something about the 3 planes. They are not interacting the way you'd like them to if you want to get a unique solution. So when you're looking at an example like this, you don't have to write it as a matrix. I will just say our book writes these all as matrices. So because once you have a matrix, you can then identify the rows. You can be specifically talking about the row operations you need, and you want to write this in REF. So hopefully REF is going to look like this. I'm just going to put little variables here, A, B, and C. That you'll get 1s along the diagonal. Once you have the 1s along the diagonal, you get 0s below each of the 1s, and then your third equation will tell you what the third variable is. In this case, is Z. Once you know Z, you can figure out Y. Once you know Z and Y, you can figure out X. So the row operations will produce, hopefully, this matrix in reduced echelon form. Sorry, row echelon form. I got ahead of myself there a little bit. If you want to do one more step, different matrix, reduced row echelon form, which is abbreviated REF, would look like this. It takes reduced echelon form and takes it one step further. Our author likes to use stars to denote things that can be anything. I don't know why that is, but that's the way to do it. So this is considered to be reduced row echelon form. You can see a big advantage if you have the matrix in reduced row echelon form. No back substitution is necessary. This is Z, this is Y, this is X. Now, what's the trade-off here? If you're doing these by hand, you will need 1, 2, 3, 4, at most 5 steps to get into row echelon form. If you want to get into reduced row echelon form, you have to get a 0 here, a 0 here, and a 0 here in addition to everything else. So that's additional 3 more steps. So if you're not using technology here, it is a more lengthy process. However, once you have it in this form, you can see exactly what your answers are going to be, and that's the part that'll take much less time. So let's save us a little bit of work here. Let's go to the calculator. Always love switching back and forth between screens here. And let's go with our first matrix here, which is a 3x4. And I'm going to type in the coefficients that you saw on the screen there. So we have 1, 1, 2, and 9. That's the first row. Second row is a 2, 4, -3, and 1. And then the third one is 3, 6, -5, and 0. Okay. So this is the part I remember I had told you in class, I don't like this feature of the calculator. If you don't exit right now, you're going to mess up your entries. So I always quit it after the matrix has been entered. And then you can go back to matrix A and just ask it to display it for you to make sure everything was typed in correctly. So 1, 1, 2, 9, yes. 2, 4, -3, 1, yes. 3, 6, -5, 0, yes. Okay, so once your matrix is in there, there are the matrix operations. And the ones we're going to use here, even though you can do the row operations, as I said, you can swap rows, that's Command C. You can add a row to another row. You can take a constant multiple of a row. And then this is the one you would use by taking a constant multiple, adding it to another row, and replacing that row. Well, let's get the 2 matrices here. So row echelon form for matrix A. Looks like that. So there it is. If you don't like the bunch of 6s here, I think you remember how to do this. Change everything to a fraction. So there's your fraction form. So right away, you know what z is equal to. Z is equal to 3. And then if z is equal to 3, you can consider this as an equation. Y minus 11/3 times z is equal to -9. Put this in for z and determine y. Put z equal 3, whatever you got for y, and determine what x is equal to. So this is REF. So 1's along the diagonal, 0 is all below that one. And if you want to take it one step further and get the actual solution here, oops, didn't do that. And I'll just get RREF here real quickly. I say quickly, but it seems very cumbersome at times. Okay, so this will give us zeros in each of these 3 slots as well. So taking it the one step further. So by doing this by hand, 1 step to get the 1, then get your zeros. Another step to get the 1 here, get your 0. And then if this is not a 1, you make it a 1. So 1, 2, 3, 4, 5. I think I said 5 steps before. It's actually maximum of 6. Depending on if you had 1s before. And then the other 3 slots, 2 zeros. All right, so our REF will give us the values for A, B, and C. So x is equal to 1, y is equal to 2, and z is equal to 3. So I'll go back to the whiteboard here and write that down. And Gina, I couldn't remember, are you a Desmos person or a 84 person?
84.
84, okay. So this will be more helpful to you. Others that use Desmos can figure out how to do it on Desmos. So here is our REF. technology aided. It was what, 3, 2, 1? Is that the, or 1, 2, 3, sorry. So you can write down your solution: x equal 1, y equal 2, and z is equal 3. So this is essentially what you're doing in the second section as well, when we talk about Gaussian elimination. If you're doing Gaussian elimination, you're essentially writing the matrix in row echelon form. So you're going from the original to this form right here. If you want to take it the one step further and write it in reduced row echelon form, I think this is consistent in vocabulary. It's called the Gauss-Jordan Method. And not Jordan, it's Jordan. And that's if you use the R. Yeah. So that's the difference between the wording here. So in row echelon form, you do the back substitution. In reduced row echelon form, you pretty much write out the answers. So in this first chapter, you do want to show your row operations, and then later, of course, for the systems that have lots of variables in them, we're going to be using some technology there. So that was one of the theorems we had talked about from the textbook on Tuesday. I'll identify it using the same numbers as the textbook. It's 1.2.1. Essentially says that each matrix initially set up to solve a system can be reduced to row echelon form RF using elementary row operations. So whether you set it up as a matrix or you just set it up using the equation that you see here, if you're using elementary row operations, all systems can go from here to here. So that's a theorem. Now, the way in which you get there might vary. You might be switching rows around. It all kind of depends on where the ones are, where the zeros might be. So the way you get there, you know, if this is point A and this is point B, we might start at point A. I might take this path to get to point B. You might start at point A, take a different path to get to point B. But we all end up in the same place. This is row echelon form. So I think ideally, you would like to take the fewest number of steps possible. You might not know that in the beginning. Actually, I guess the fewest number of steps would be put into the calculator. But if you're doing it by hand, you know, as I said, a maximum of 6 steps to get it into row echelon form. So if you have row echelon form, you should be able to solve that system of equations. You should also be able to identify, once the matrix is in row echelon form, is there a unique solution? Is there no solution, inconsistent system? Or is there going to be an infinite number of solutions? So Gina, if you want to take a screenshot here, I'm going to erase this and look at a couple of other matrices.
That's very good.
Thank you. I either need to write smaller or need to make the whiteboard bigger. I don't know if it's possible to make the whiteboard bigger. That is not possible. Okay, so here are some matrices in REF. All right, so there's the first one. Here's the second one. And this is not a number, that's my way of separating the coefficient matrix with the, sometimes called the solution vector. Here's your second one. And then here's your third one. So if you look at the first one, we have essentially three unknowns. There are three rows, so one row per unknown. And notice that this is not just in REF, it's actually in RREF. And from this, you can tell that there is a unique solution. You can just write down third variable is 4, second variable is 2, -2, and the first variable is 5. So a unique solution exists for this one. Okay, in the second matrix, you look at the first row, look at the second row. You'll notice the third row on the left-hand side has no entries that are non-zero. All these entries are 0. That is an indication of an inconsistent system. So this equation is essentially telling us that 0 is equal to 1. False statement. So this is an inconsistent system because of that last row. A term we're going to use later in, I think it's later in this section, is the idea of rank. So we'll define that later, but these two matrices have different ranks, as you probably would have guessed. It has to do with the number of ones you see here. So I'll just tell you right now, I'll define it later. The rank of this first matrix is 3. The rank of the second matrix is 2. The rank of the third matrix is also 3. But what's the difference between the first matrix and the third matrix? They both have 3 rows, but this one has 4 columns. So the number of columns tells us the number of variables. So in this particular case, 1, 2, 3, 4 variables, but only 3 equations. When you have more variables than equations, a unique solution is not going to exist. A solution will exist though, but you're going to need a parameter. So right now you can tell in the third equation, if we're going to use x sub 1 through x sub 4 as our variables, the third equation tells us that x sub 3 plus 3 times x sub 4 is equal to 2. Now, because of this, you can select either x sub 3 or x sub 4 as the parameter. So because there's no column that has a 1 in it for x sub 4, usually that's your parameter choice. Because if you look here, the first 3 entries here almost kind of form our REF matrix. And it's only the last column that has the problem. So usually that's where the parameter is going to be selected. So we're going to select this as the parameter. So I'll call t. So we're going to let x sub 4 be equal to t. And that means that x sub 3 is going to be 2 minus 3 times t. And then you can write the other 2 variables in terms of the parameter. So this would be x sub 2 is equal to 2 times t sub x sub 4, sorry, which we call t, equal to 6. So x sub 2 is going to be 6 minus 2t. Then x sub 1 is going to be -1 minus 4t. So everything's written in terms of the parameter. So the rank of the matrix and the number of variables the matrix has will help us identify, first of all, whether we need a parameter or not and how many parameters we're going to need. So in this particular case, we just need the 1 parameter. There's kind of, I'm going to put this in quotes. You can, certainly program a computer to do this, but there's an algorithm for what they call Gaussian elimination, which is essentially the row operations on the matrices. It's elimination, not elementary. It's in section 1.2. I don't know exactly what page it's on because the page numbers are a little messed up, but it's essentially saying you want to get it in this particular form. So I got to get a 1 in this slot, and then I got to get zeros below it. Then I need to get a 1 in this slot and get a 0 below it. Then I got to get a 1 in the slot. that also is working here. Once you have all of those operations done, your matrix will be in for echelon form. So as I said, number of steps varies. You can swap your rows around, looking for the ones that are already there, but it's a nice systematic way to produce a matrix that essentially will look like this. If you started with a 3x4, for example, that's going to look like this. And that's how you can certainly program a computer to do it. But the computer doesn't mind working with fractions and things like that. So there might be a more convenient way to do it where your calculations are a little less dependent on fractions. So anytime you have a row that looks like this, your system will be inconsistent. You essentially think of it as 0 is equal to some number that's not 0. So here's another general statement you can make about this situation. So in general, the number of leading ones, they call them leading ones. So these are the ones you see all the way to the left in a particular row. So these are all leading ones here. These two are leading ones, and these three are also leading ones. Are the same in your your row echelon form. So what that means is the way you get there, it doesn't matter. It's actually the matrix that you start with itself that's going to tell you what your REF looks like. So the method to get there does not matter. So two ways to get from point A to point B. As long as we're all at point B with our REF, we're in good shape. I'll give you a chance to do another screenshot here, Gina, if you want to. We're going to talk a little bit more about the rank idea again.
Very good.
Okay. So going back to this term rank, we're going to actually define it and see how it is going to help us predict and write down what the solutions are to some of these systems. Okay, so here's the definition of rank. The rank of a matrix. Now the matrix we're talking about here is the matrix of coefficients, so not the augmented matrix with that extra column for the answers. So the rank of a matrix, A, is the number of leading ones in row echelon form. So all those ones you saw on the previous screen, we identified the rank. So going all the way to the left, each of those rows, the number of ones you saw there, that gives you the rank. So the first matrix had a rank of 3. The second one had a rank of 3, or no, rank of 2, and the third one had a rank of 3. So when you're looking at those systems, if you have a row of zeros, let's take this matrix right here. Now A would be this matrix right here. So the rank of the matrix is going to be 2. And that's because you're looking at these two ones right here. So that's going to give you a rank of 2. Now in this one, however, there are how many variables? There are 3 variables. We've seen before that if you have a row of zeros, we have an infinite number of solutions. So if we think about these 3 planes, they're all actually going to intersect a line. One plane was actually a constant multiple of another. So they're going to intersect in a line. So if this number is larger than this number, infinite number of solutions. If these two numbers are the same, one answer. So that's a theorem in the book. I think you can see it in these particular examples that we're doing here, but this is kind of the general statement for the theorem. If you're given a system with m equations, so m equations, we have 3 equations, and then n variables. So this one has 3 equations and 3 variables, so those 2 numbers are the same. And your solution is consistent, meaning there is a, your system is consistent, meaning there is a solution. And then the rank of the matrix, we'll just call it R. There are 2 things that can happen, as I just said. If R is equal to n, if these 2 numbers are the same, so the rank is the same as the number of variables, you get a unique solution. However, if you have more variables than the rank, so in this case, if the rank is less than the number of variables, you're going to get an infinite number of solutions. The other thing that's going to happen here is if you know there's an infinite number of solutions, you're going to need a parameter. How many parameters are you going to need? The number of parameters is determined by these 2 numbers right here. It's all part of the same theorem. It's n minus r. So if you have 3 variables, which rank is 2, you're going to need 1 parameter. So I think you can see in this particular system, there was, when you did the row operations, 2 of the planes ended up being constant multiples of one another. So this is our new system. The last row is 0 is equal to 0, don't need to include it. So here, once again, is going to be your parameter. So using, in this case, z, called t, and you're only going to need the 1 parameter to describe both y and x. So these results right here, if we think about them in general, this will work for any value for n, any value for r. Now, so sometimes in the abstract, you're looking at lots of these letters and you're trying to figure out what the letters are representing. So if you go back to an actual example here, rank 2, 3 variables, we need 1 parameter, which is 3 master. So if we had a rank of matrix of 4, but there were 7 variables, you would need 3 parameters. So you'd have to set those 3 variables using STM, whatever you want to use there, and then write the other variables in terms of the parameters. So independent of the system, if you know these 2 numbers right here, you'll know how many parameters you're going to need. All right, looks like I'm out of room again, so I'm going to take another picture here.
I'm good.
Right. So in the last section that actually does something that's not an application, we work with what are called homogeneous systems. And I think we talked about this term on Tuesday. The definition of a homogeneous system is all equations are equal to 0. So that last column you're going to see there, you put it in a matrix, all going to be 0. What that means is if you have a system in which all of the equations are equal to 0, just throw it out here in 2 variables. When you do the row operations, are these numbers ever going to change? You're taking a multiple of one row, adding it to another row, 0 times the number is still going to be 0. So no matter what happens here, these two numbers are not going to change. They're going to be 0 and 0, true for any number of variables. So here, if I want to write this in REF, or even RREF, that's what it's going to look like. So I can add 2 times the first row to the second row. That's going to get my 0 here. I don't know if this is going to be a 1 necessarily in the beginning. 2 times y, 4 times I get a 6. And then I can just divide everything by 6 to produce REF. Remember, REF has 1s along the diagonal. So this is like one step before row echelon form. So what is y? 0. What is x? 0. Surprise, surprise. Didn't have to solve a system, use any row operations to know that 0, 0 is going to be a solution. The systems that are homogeneous that have what are called non-trivial solutions, this is a trivial solution, are the ones we're actually more interested in. So which homogeneous systems, is kind of an open question, which homogeneous systems will have non-trivial solutions? So something where the variables are not all equal to 0. Do you think it will ever happen if we have the same number of variables as equations? No. All your REFs are going to look exactly the same. Whether this is a 1, whether this is a 0, not going to matter. If this variable is 0, this variable will also be 0. So if we have the same number of equations as variables, no, not going to happen. So the only way you're going to get a non-trivial solution is if you have these two numbers to be different. So more equations than variables, more variables than equations. So that's actually a theorem in the book. I wrote down the number here. I think it's 1.31. The numbering in our textbook is, I think they do the section number, and then this is the first theorem in section 1.3. So this is the theorem. It says if a system has m equations and n variables, and the number of equations is greater than the number of variables, then a non-trivial solution will exist. And the other thing to take away from this is we say, okay, it's a non-trivial solution, meaning it's not all zeros. Is it going to be a unique solution? No, that's not going to happen because we have more equations than we have variables. So this is when you're going to get the non-trivials. So let's do an example. I'm going to need a lot more room here. So I'm going to take another picture. I have a 5 variable system with 4 equations.
Got it.
Right. So let me write down the system here. And we're going to use x sub 1 through x sub 5 for this one. So it's 2x sub 1 plus 2x sub 2 minus x sub 3 plus x sub 5 is equal to 0. Negative x sub 1 minus x sub 2 plus 2x sub 3 minus 3x sub 4 plus x sub 5 is equal to 0. X sub 1 plus x sub 2 minus 2x sub 3 minus x sub 5 is equal to 0. Then x sub 3 plus x sub 4 plus x sub 5 is equal to 0. All right, so you can see we have 5 variables, but we only have 4 equations. So a number of variables exceeds the number of equations. So when you set this up as a matrix and you try to get into REF, we're not going to be able to get just a bunch of ones along the diagonal because of the number of variables. So here's the original matrix. And I did save a little bit of time on this one. I do have REF. I'll show you in a minute. But this is your original matrix. So right away, you can tell, first of all, it's a homogeneous system. All the equations are equal to 0. And also more variables than equations. So the best you're going to do for REF is get ones right along here. That's the best you're going to be able to do. Let's circle that for you. So with this number of variables, doing it by hand, it's going to take a while. Let's use the REF that I got from the calculator. But you'd have to get a 1 here first. You can swap rows if you want to. Get a 0 here, 0 here, 0 here. That's 4 steps. Get a 1 here, 0, 0. 3 more steps. Get a 1 here, 0. 2 more steps. And then finally get a 1 here. So if you are doing it by hand, those are the steps you would follow, but I'm going to give you the REF here without you having to do all that. So I'm going to ask you what the rank of this matrix is, ask you how many parameters you're going to need to write the solution of the system out. And then we're going to write down a general solution. So there's REF for that matrix right there. Now, if you want to practice, putting in the calculator, see if you get the same thing, that's perfectly fine. But these numbers, as I said, are not going to change. So what is the rank of this matrix? How many leading ones do we have? 1,
3.
2, 3, exactly. So the rank of this matrix is 3. But how many variables are there? 5. So how many parameters? Going to need 2 parameters. Now, you'll notice that the 4th row is all zeros. So you can pretty much ignore the 4th row. It's not going to matter. If you look here, x sub 5 is going to be one of the parameters. It's called t. What's the other parameter going to be? The third equation tells us that x sub 4 is equal to what? Actually 0. So that's not a parameter, that's equal to 0. The other parameter is going to be right here, because the second row tells us that x sub 3 is equal to the opposite of x sub 5. So we can call that negative t. But x sub 2 can't be determined any other way. So x sub 2 is going to be our other parameter here. I'll call it s. And then x sub 1, we can write in terms of the 2 parameters, s and t. So it's going to be negative t minus s. All right, so there's our general solution for this homogeneous system. So something that's kind of previewing a concept we're going to be talking about later. There's a different way to write this. You can write them as column matrices. So we can't really use ordered pairs anymore, ordered triples. We have a larger number of variables. So you can write it out this way. What is x sub 1 equal to? negative s minus t. What is x sub 2 equal to? S. What is x sub 3 equal to? Negative t. What is x sub 4 equal to? 0. What is x sub 5 equal to? T. So you can write it in what we call column matrix form. But one reason for doing it this way is we can write it as what's called a linear combination of two unknowns, s and t. And the reason this might be a better representation is it gives you a way of identifying what your parameters are going to be and write them as multiples of two particular solutions that are going to work in the original equation. So s times -1 plus t times -1. That's what x sub 1 is. X sub 2 is equal to s. So s times 1 plus t times 0. X sub 3 is equal to negative t. So we have no s's and then -1 times t. X sub 4 is 0. So no s, no t. X sub 5 is t. So once again, no s and then 1 t. So what you see here, our book calls these basic solutions. These are non-trivial solutions to a homogeneous system of equations in which a general solution is based on. Meaning if I take multiples, what are called linear combinations of these two column vectors, I get a solution to the original system. So if I say s is equal to 1, for example, try to make the numbers easier, and then t is equal to -1. Here's a solution. S times 1 plus t times -1. So -1 times -1 is 1. So one solution would have x sub 1 being 0, 1s plus 0t. There's your x sub 2. And then for the third one, s is always going to be 0, so we can ignore that part. And then second component says -1 plus, sorry, -1 times -1 produces a 1 there. Third one is going to be 0. Sorry, fourth one is going to be 0. And then last one is going to be t, so t is equal to -1. Okay, so what you see right here is a solution to the system. So this is your x sub 1, a particular solution. This is x sub 2. This is x sub 3, this is x sub 4, and this is x sub 5. So if you want to go ahead and check it, it should work. So there's a nice way in which we can write, using the number of parameters, this idea of what we call a linear combination, using the parameters as variables. So I take a multiple of this column vector and a multiple of this column vector, add them together, that's going to give us a particular solution to the equation. So the number of parameters we can get from the rank and the variables. The number of basic solutions is essentially the number of parameters. So for each of these types of problems, you can write your solution this way. I do my best to try to make my t's and pluses look different. That's why my t's have a hook on the end. But my pluses sometimes end up having a hook on the end too. So sorry about that. So the book introduces this idea of a linear combination of vectors. So you're taking a multiple of one vector, adding it to a multiple of another vector to produce a third vector. Now you can have as many vectors here as you want. You might have 3 basic solutions. We would need 3 parameters. A couple of the exercises are asking you to determine if one vector is a linear combination of these other 2 vectors. Let's take a look at that example. So I'll go ahead and do a screenshot here, Gina.
Got it.
Okay. So you can see how these questions are kind of related. If I write down this original vector, our original, I'll just call it a column vector. Is it possible to write this vector as a linear combination of these three vectors? So let's call this one, let's call this vector W. We'll call this vector X. We'll call this one vector Y. Oh, Gina, I can't remember. Did you have Calc 3?
Yeah, I did.
You did, okay. So you're familiar with vector notation. You know that when you write things out as vectors, you have to use the arrow notation because it's impossible for me to determine whether it's bold or not bold. That's how a lot of textbooks write them. So
Yeah.
anything that I write on the board that's a vector will have the vector notation with the little arrow over it. If I can make this bold, if there is a way to write something that's definitely bold, it'd be a lot easier to do. But A, B, and C are scalars. W, X, Y, and Z are vectors. So this is actually a question. So is W a linear combination of the other three vectors, X, Y, and Z? So a little different question than what we did on the previous example, but we're going to see how a system of equations is going to help us out here. Because in order for this to work, we need to find constants A, B, and C multiplied by these vectors, column vectors that you see here, to produce the column vector W. So what is the first entry telling us? 0 has to be 2 times A, 1 times B, 1 times C. There's a 3-variable equation. Do the same thing for the other two entries. 1 is going to have to be 1 times A, 0 times B, 1 times C. So there's your second equation. Do the same thing for the third equation. -3 is going to have to be negative A plus B minus 2C. So now the question reduces to, does the system have a, now key word here is unique. We can't just have an infinite number of solutions. We need constants A, B, and C that will produce this vector right here. So it's got to be a unique solution. Well, we have 3 variables. We have 3 equations. Here is the matrix, and it's not the columns that you see here necessarily. When you set it up, A, B, and C become the new variables, but you can see the first row is going to be the first row you see here. Second row is going to be 1, 0, 1, 1. Third row is going to be -1, 1, -2, -3. So if that system has a unique solution, we will know what it means here. And that's the answer to, will vector W be a linear combination of these vectors right here? We've done enough of those on the calculator. Let's actually do this one by hand. We've got 5 minutes. I'm going to swap a couple of rows here. I like the 1, 0, 1 to be the first row. I'm going to put this as a second row. And drop this one down, make it the third row. So now I can just add the first two together. So 1 plus -1, 0 plus 1, 1 plus -2, and then 1 plus -3. Then I'm going to take -2 times the first row and add it to the third row. So I'm going to try to do this without writing it down. Sometimes not a good idea, but let's see. -2 plus 2 is 0. 0 times -2 is still 0. -2 times 1 is -2. -2 plus 1 is -1. And then -2 times 1 is -2. -2 plus 0 is -2. And guess what? Row 2 and row 3 are exactly the same. So the next step would be essentially taking -1 times the second row, adding it to the third row, and we end up with a row of zeros. So your new third row looks like this. Okay, so this is the advantage of actually, I could show you the steps and write down what the row operations were, but me actually explaining it as I go through the steps, I didn't write everything down, but you can see what I did. Swapping row 2 and row 3, making row 1, row 3. Taking the first two equations, adding them together, taking the first equation, making a 0 in this slot right here. So I actually did row 1 plus row 2, that's the new row 2, and then -2 times row 1 plus row 3. And then this one was just the opposite of row 2 plus row 3. All right, so does a unique solution exist? No. So what that means is it is not possible to write this vector as a linear combination of these given vectors. Okay, I don't have time to write this on the board, but Theorem 1.3.2 in the textbook essentially summarizes everything that we have just done here. I'll quote it for you here. A is an m by n matrix. Rank of A is R. You have a homogeneous system. The system has n minus r basic solutions, which is the same as the number of parameters. Other solutions are linear combinations of the basic solutions. So that's the kind of big result from section 1.3. It has to do with homogeneous equations. So I'll just write this down. N minus r basic solutions. Others are linear combinations, LC, of the basic solutions. So that last example we did is helping you understand the result of this theorem. All right, so one more screenshot for you there, Gina. And as I said, if you want to take a look at a couple of those applications from 1.4, 1.5, and 1.6, there was no lyrics homework specifically for those sections. So those are pretty much ones you have to set up on your own. So I did one example from each section, put them in the notes, so that hopefully will be enough to do weekly homework for that, because you won't have any lyrics homework to help you out there.
Sounds good. I got it.
Yeah, okay, great. Any other questions or?
Nope.
Anything looks good? So on Tuesday, we'll continue, maybe do a couple more examples from chapter 1, see if you have any questions on the lyrics homework, and then start talking about matrix algebra, and then how that's related to our Gaussian elimination.
Sounds good.
Have a good day. Stay warm.
You too.
Stay safe. Okay. I'll see you on Tuesday. See everybody else on Tuesday as well.
Okay.